Okay, let's take a look at lesson 3.6, a quick review of the chain rule, plus I'll do a couple of examples at the end. Now the chain rule, again, is going to be a process we just kind of memorize and learn how to do. It comes from some, again, where it says deriving the chain rule. Again, math majors want to play with this, looking at and taking some time to look at how we use the definition of the derivative, the limit definition, to see what patterns emerge, right? And so you can see a proof here or a derivation of the chain rule, right? In the end, though, it really is this idea of calculating the derivative or finding the derivative of a function, right? When a function is within another function, which we call a composition. We don't appreciate composition of functions very much in like previous classes, but it really plays out here in the chain rule, being able to recognize when I have a function inside of another function. And that's that notation, right? It looks like fog of x, f of g of x, meaning g of x is inside of a function. And again, this is in the world where somehow we have these interactions between these patterns, right? These functions, and then we realize that one function is acting on another function, right? The patterns are interacting in some way. And so we have the notation here of a derivative, which is f, this is the more classic way, f prime of x equals f prime of g of x times g of x. And the way I see that is, this is the derivative of the inside, right? G prime of x. You take the derivative and then multiply that by the derivative of the inside. Now we have Leibniz notation here, which doesn't make sense sometimes because we don't see the substitutions, but we're going to use substitutions. We use them often in calculus by substituting single variables to represent functions. And this becomes helpful for that when we get there and look at something like that. Problem solving, you can read that, but it really is about recognizing I have a function inside of a function. And so what I mean by that real quick, let me see if I could come up with something here as we look at that, right? You need to be fast at recognizing this. There we go. So looking at the difference between some functions here. Let me write something on the right side over here. So you should be able to recognize the difference, right? Let's say something like that, right? X squared plus sine x squared, something like that. That's, again, a sum. I don't see that is different than a quotient rule. A product rule. And that is different than sine x squared over x squared, right? And that's different than just the sine of x squared, which this is, right? Sine of x squared when we think about it, right? Those are different types of functions. You have to recognize the differences between all of those. Each of those are different functions, and we would approach those differently, right? This would be a chain rule. Now, when we take the derivative of this, we would actually have to employ or use the chain rule. So I know you can get confused a little bit. It's like the chain rule is what we use to calculate the derivative. Where's that function here? Of a function, we have a function inside of another function. Product rules, right? There's just a formula we use, the order that we take the derivatives, right? So it's not really taking the derivative of product rule, right? Or a quotient rule. It's telling you the order. When we use the chain rule, we're taking the derivative, right? We're calculating the prime. Versus on a product rule, right? We're not taking the derivative. I want to make sure that's clear to you as you go through that, right? As we think about if you were going to take the derivative of this one here, right? If you had f of x equals x squared sine of x squared, right? If we had something like that, that's a product rule, right? And so what you would say is there's your u, there's your v, or something like that. You can say something like that. And then we know that f prime, the product rule, is just telling us the order to take the derivatives, right? U prime v plus v prime u, right? And then when you take the derivative, right, when you say, okay, what is u prime 2x v prime? That's when you're going to use the chain rule, when you're actually taking that derivative, right? And so that becomes cosine x squared times 2x, right? So as you look at that, I want to make sure you're clear with that as you start to figure out and kind of go through product rules, chain rule, quotient rules, power rules, all those things. So you can see here's a great example of, again, as we look at this here, there's a function inside of this here. So you have 1 over x would be one function, and then you have 3x squared plus 1 squared inside of that. And so I see a function inside of a function here, though they changed it into a power rule here, where you're going to then take the derivative, right? You can see -2, and then you keep the inside function, -3, and then derivative of the inside function. Again, really looking at the notation of those. I'll do a couple more examples for us, though, as we look at that and go through it. And then the chain rule applies to trig functions, kind of like the one I was showing you, right? Looking at sine cubed. I did sine x squared. The x squared was the function here. The sine x is the function inside of x cubed. If you look carefully here, right? If you really look at, let me annotate real quick. If you really look at this, again, it's really about identifying what we have here. So if you look here, this is again how I see it, right? You have sine cubed x like that. What you have though is h of x equals f of g of x, and you have to identify what's your f and g. In this case, your f is x cubed, your g is sine x. So when you plug g into f, you get what? You get sine cubed x. And so that's what we're playing with here as we start to think about the chain rule. You start to identify functions inside of functions here. Okay, I'm going to annotate that, clear, get that out as we look at that there. And again, everyone has their notation. That's why it can be kind of difficult. You're looking at multiple textbooks, using the Khan Academy, looking at Trig or whatever. Everyone has their different notation, but you can see 3 times sine x here, right? Squared times the derivative of the inside. We just need to practice some of those. You can look at solutions here. You rewrite that as a -2 potentially, and then you don't have to use a quotient rule, which you could. Let's see, combining chain rule, that's where chain rules with other rules. You can see here, this is a cosine, it's not a power, right? But again, I have a function inside of the cosine, right? So it's going to be negative sine of the inside, 5x squared, times the derivative of the inside. As you can see, your g of x is the function inside of the cosine, right? It's inside of the f of x, and then you go with your formula, right? So again, looking at a quick annotation just to explain the formulas here, right? In this case, I have your f of x equals cosine x, g of x equals 5x squared. The derivative, right? H prime of x would be equal to f prime g of x times g prime of x. That's our notation. So when you take the derivative of f, right? F prime of x equals negative sine x. But what am I plugging into the derivative? G of x. G of x is 5x squared. And so that's where you get your negative sine 5x squared. I'm plugging g of x into the derivative times g prime of x. G prime of x equals 10x. And there you go. So that's the long way to look at it, not the wrong way, the longer way to look at it. And then you start to see patterns. Let's continue on. Again, then you can use these trig functions, the derivative, secant, right? And then you apply your rules there. Chain rules, again, work with trig functions, and that's what we were looking at. So take a look. I kind of prefer this notation here. It's cleaner to me, but again, this is the one that gets used more, I think. The derivative of sine of u being some function equals the cosine of u times the derivative u with respect to x. Again, I appreciate that notation, so let's take a look at it. It's cleaner to me. Let's say I found, I want the derivative of sine, the one I did earlier, right? X squared, right? What does that equal to? Well, what we need to do is we need to say, okay, u equals x squared. The derivative of u with respect to x equals 2x, right? And so the sine of u, so now we have the sine of u is cosine u. U is x squared times du dx times 2x. I like the u substitutions for that, but again, we have the composition functions too, notation there. Something to look at and think about as we go through those, as you look at those examples there. Here's a product rule. Then, so do you see how when we look at this, the way I kind of see this one, when we look at this, a different color, right? I would say, okay, there's your u, there's your v, or you say there's your f and g. H prime of x is going to be u prime v plus v prime u. And then you calculate, there's your u, there's your v. You say u prime equals 5 2x plus 1 to the power of 4 times 2. V prime would be equal to 7 3x minus 2 to the power of 6 times 3. And then once you have that, then you go ahead and so you can follow this notation, right? Then see how I use the chain rule here, and then you just substitute in what is h prime of x going to be equal to? What's u prime? What's your v? What's your v prime? What's your u? And you put it all together, and then it simplifies that. This one turns out, make sure you learn how to factor that out and see there's a common factor in here. The 2x plus 1 and the 3x minus 2 can be factored out. So keep that in mind. Again, the different ways to write this. Compositions of 3 functions, rarely do we see that, but sometimes it's just fun to play with that and you could follow that process. But again, it's a step-by-step piece. You go through it. I think that would be it, other than, trying some problems and doing more as you look at the different derivatives and chain rules and looking. I guess we can end on one more here. Doing this one together here, sine 6. So again, how do you see that? There's multiple ways. Someone says, I see f of x equals, and so you see multiple things going on here. F of x equals sine x. I also see, you can then see, I have, well, actually, f of x equals x to the 6. G of x could be equal to x to the 6, sine x, and then you could have another one, j of x is equal to x cubed. So what you see here is I see h of x is equal to, it doesn't have to be this complicated, I'm just showing you how it looks, right? It's, you have x to the 6 equals f. Inside of f, you have G, and inside of G you have J. So it looks like that, right? It's the compositions, but sometimes you start to see the pattern. Okay, so what do we have here? We have sine x cubed to the power of 6. So another way to think about, there's your u. Okay, you're in here and you have a u, right? And you're taking the derivative of u to the power of 6, right? U to the power of 6, if you think about it. So that'd be another way to look at that. If you say, okay, u equals sine x cubed, okay? And so now what is this function here? What is h equal to? H is now equal to, we use u notation, u to the power of 6. What is h prime going to be? It's going to be 6u to the power of 5 times u prime du dx. And then you calculate the derivative of this one here, right? What is u prime equal to? Well, u prime is sine x cubed, which is going to be cosine x cubed times 3x squared. And then that's what you would put in there. So your h prime is just going to be 6 u to the power of 5. So that would be, my writing's bad, sine x cubed to the power of 5 times cosine x cubed times 3x squared. I know it doesn't follow nicely. Again, just thinking about how you think about it. I see, again, a function inside of a function, right? Inside of another function. So just kind of playing with that as you do that there. And of course, you had the example up above to do that. Clear out of here. Let's go ahead and take a look here. And again, as you can, just different ways to kind of apply a lot of that stuff. I think that would be it. Hopefully that cleared up some of the stuff, not too crazy. Just want to double check as we look at that. This is always, again, a fun question here to kind of play with. It goes with your notation, so make sure you look at that. And then, of course, we'll play more with Leibniz notation as we go on. It becomes a handy way to look at stuff.